Okay, so thank you all for coming. I'm Alfonso Rodriguez, and I also work at the Centro de Electrónica Industrial here in this building. And I'm going to try and provide an overview of this adaptive reconfigurable computing thing and why there is a need for a support at both design and runtime. Basically, the context for this comes from cyber-physical systems, and also in which there is a change in the paradigm. So computation applications are moving from simple scheme of just sensing whatever and measuring, for instance, temperature or humidity, to a scenario in which the computation needs to be moved to the edge, for instance, in drones or even in autonomous vehicles. But also we have this special fact that the task is independent from the requirements. For instance, I need to compress an image, but I need to do so taking into account the energy budget that I have. So there's this independence. So we try to address this problem using hardware acceleration and more specifically using FPGAs. We provide a special feature that is dynamic and partial reconfiguration, which basically is I'm able to copy and paste circuits inside my chip. So this renders a software-like flexibility and the performance that we can achieve using dedicated hardware logic for the computation. Also, this hardware copy and paste provides certain levels of adaptivity, or can be used to improve the adaptivity of the system. And basically, the proposal of this thesis is a framework that you can barely see. Basically, it provides at the top a toolchain that provides a way to describe your application in C, C++, and then generate both the executable that is going to be running in software and the dedicated hardware accelerators that are going to be changed in the FPGA. This is the hardware flow, and this is the software one. And then there's the runtime support at the bottom that provides an interface between the running application in the processor and the accelerators. And these accelerators are placed in Artico Cube, which is a reconfigurable architecture that allows designer to work with trade-offs on runtime between execution time, so performance, energy consumption, and also different levels of fault tolerance. So for instance, you can have different accelerators performing computation on different sets of data, but you can also provide the same data to a set of accelerators and vote the result to enhance the dependability of your system. And on the right side of this picture, there's actual measurements that we took in one of our test applications, and even taking into account the energy spent during reconfiguration, which is this. That is something that you don't have when switching tasks in software, for instance. At the bottom, you can see the comparison between the same computation being performed in hardware, it's the blue one, and in software. So this proves in a way that these kind of approaches make sense, especially when you are dealing with computing-intensive tasks that have significant levels of data parallelism. And that's pretty much it. So thank you again.